No problem here.
Yeah, Sellard, for example, said that he was looking forward to that. He wasn't able to join today, but was interested in getting the recording.
Great, good. I think we're pretty stable, actually. I think we've got about 18 folks on, and I have managed to figure out how to turn off the waiting room. So if you'd like to kick it off.
Okay, CJ, do you want me to go, or
yeah,
how do you want to do this?
Jump right in. So I guess I could just say that we have been working on some HiHAT infrastructure and obviously been listening to this. Found fascinating a number of the issues that you guys had worked through and brought up. Really appreciated the level of detail you went into last time. We had some discussions internal to NVIDIA about, hey, what's this? How's this work? Where are we going? Here's some related things that we've done. Maybe we wish to talk some more about those, and so I thought we could dive in to a little more detail. So I think our observation is that even if we're not sharing code, that sharing idea around requirements and what some of the real problems are and how we want to work through those is interesting and mutually beneficial. So we're delighted for all the folks that are here.
Yeah, that sounds great. Okay, so CJ and Wilfred came to us, messaging us a bunch of questions that came after the previous HiHAT meeting. And so Alex put together some of these slides, which I worked with him and as well as Waleed. And so before we jump into the questions, I thought it'd be beneficial to give a quick recap on what we are doing. So the library that we're working with is called Hedgehog, that we've been continuing to develop in the past year or so. It's based on data flow. So for example, here's a data flow graph where kind of these are the nodes, and then there are different types that are feeding into the nodes, and the nodes will be producing potentially a different type. What's unique about this is that we take advantage of data pipelining by attaching threads to essentially each of these nodes. And you could have potentially multiple threads where you will clone the node and bind a separate thread to each clone. And that effectively increases the rate at which these nodes can process data. So the data pipelining is effectively allowing us to be able to overlap some of the more compute intensive parts with the IO pieces. And so that's how, if not all of our performance. So one thing to keep in mind is that the kernels that are being run within these tasks are persistent. And so when a thread is spawned to run a particular task, it will live throughout the entire life cycle of the graph. So the graph, that thread will persist, and that kernel that it's running will also persist until the input has been terminated. So the way that we fire these tasks is based on data. So these edges contain a queue, which is a data queue. As soon as data is inserted into that queue, we will essentially signal the task to tell it to wake up and process that data, and it will dequeue one of the items and then and work with it. We focus mostly on coarse grain parallelism. We rely on compute kernels to provide us fine grain parallelism. So a task could use on the internally something like cuBLAS or OpenBLAS to kind of get the fine grain parallelism to hit the caches and take advantage of the cores. But we mainly operate in coarse grain parallelism to kind of justify the cost of sending data between nodes, which we've measured to be around a microsecond or less. The lowest I've seen is around 500 nanoseconds to kind of get a node running with a piece of data. Everything is fully asynchronous. The schedule is 100% dependent on the flow of data through the graph. So we don't have like a global scheduler. It just, as soon as you send data in, the graph itself will just handle it itself. And we are very careful in terms of how we manage state. We don't have a global state representation. We actually have nodes in the graph that represent what we call state managers, and that represents kind of the interaction between two tasks or two or more tasks. And so it represents the local state, as we like to describe it. So to kind of give you an idea what Hedgehog looks like in the coding sense, the highlighted region shows what it would look like to build a graph in Hedgehog. This is our data flow graph, which has you specify the output type, and then you can have a list of input types that the graph accepts. You create your instances of your tasks. You add these tasks into the graph and connect them, and you get something like this out. Now, as soon as we call the execute function, execute graph, what this will do is it will spawn threads. So in the case of the batch increment task, we've told it to give it 10 threads. And so this will effectively duplicate or clone this, this instance and then attach a thread to each instance. And so those instances are going to share the same input queue in a thread safe manner. And so when the split vector task produces data for this kind of group of instances, then only one of them will, or they'll safely access that queue, pretty much. So to get things running, what you do is you push data into the graph. In this case, we're pushing an array. We'll say it's an array of 1 million elements. The split vector task is configured to kind of split that large array into blocks of 1,000. And so it will produce 1,000 data objects that kind of decompose that data. And so you have 1,000 elements in this queue here. And so all 10 threads can run through that 1,000 elements in parallel. As soon as we're done pushing our data, and you can kind of see the animation there. As soon as you're done finished pushing data, we asynchronously will kind of decrement the input edge coming into this task so that when the input edge is no longer receiving data and the queue is empty, then this thread can safely terminate. And this gets propagated so that when these input queues are also terminated or are empty, and the input edge is no longer receiving data, then these threads can also safely terminate. And the wait for termination is a way for kind of joining those threads.
Can we clarify something here?
Sure.
It's clear that the split vector task broke that into whatever it was, 10 groups of 100, right? And I think
sure.
what wasn't clear to me before is that out of these tasks 1 to 10, they're not pre-assigned some specific item to pick up. They're actually competing off of a work queue to go grab stuff with mutual exclusion. And
that's right.
That's for the sake of overall load balance eventually?
It's for the sake of lower overhead, I guess, so we don't have to schedule them. They'll, because the split vector task will signal to this group of tasks, or this group of nodes. And the signal will basically tell them to wake up, and whatever's in the queue when they wake up is going to be what they process.
So
it's going to be.
I don't understand that, because you could have had a specific dependence from the split vector task for a given subset of the data to a particular task, and they need not have competed at all. They could have all been looking for a specific piece of data, and rather than work stealing in shared fashion, right? And you chose not to do that. You, I think, could have done that.
It's actually a lot simpler.
Obvious that you could have done that in this framework, and you chose not to do it.
Yeah, we haven't had a need for doing any work stealing. When we think of things like work stealing, I guess the concern was that if we were oversubscribing or undersubscribing the CPU, such that if a task were waiting or was idle waiting and had spare cycles, then it could steal work from someone else and do computation. But we really think in terms of a thread being like attached to a specific operation in a way. So we want it to be bound to that task.
It is assigned. So yeah, each tenth is going to a particular task, and other tasks are only free to get their 10th, and that's it.
CJ, so this is Walid. Tim? I mean, in reality, sure. Ahead, sort of the way we think of this stuff is as producer-consumer relations. So the split vector task is going to produce items, add them to the queue, and then the consumer, whenever something is being added to the queue, one of the threads I mean, for now, it is typically, we don't explicitly request any particular thread. One of the threads wakes up by the condition variable that is attached to the queue is going to wake up, retrieve an item from the queue, and then will proceed to release the queue.
That sounds like work stealing, right? You're saying it's not.
It is work stealing, but it really is a very, very localized form of work stealing, so that at the end of the day, I mean, it's not a global work stealing. It is very localized to just this producer-consumer related queue.
Okay.
I guess it could be thought of as a work stealing, but I mean, we never really thought of it that way. It's just kind of, these two tasks have this interaction, and this one is going to be splitting the vector and producing kind of the iterators to tell it what range that it needs to operate on. And then all these tasks are going to be doing is the same work, the same piece of code.
And could you have just as easily had multiple producers in addition to multiple consumers?
Yes, absolutely. Yeah. So you can have all other tasks feeding into this as well if you wanted to, into this queue, if they are the same type potentially. But you could also have multiple types. So you could have the two different input types, for example. But we'll get into that. I think we'll answer some of those questions and hopefully make it a little more clear. We can also produce a dot
I hope
file.
I didn't cut you off there. Sorry. Did you have something else you wanted to add?
I mean, I just wanted to add the fact that, I mean, so our work in many ways is driven by sort of our needs for developing applications that are performance oriented. And as a result, sort of we have stayed away from developing sort of complex or overarching solutions. Sort of our solutions have remained sort of pretty closely wedded to applications that we have needed to, that are on our to-do list in a sense. So we've evolved the system, but we have avoided sort of these global ambitious solutions, let me put it this way. And but again, I mean, Tim will actually address several of these questions as we go through. All right, Tim and Alexandre. And I will try to refrain from intervening as much as possible.
No problem. Always appreciated. All right, so let's dive into the questions. So Alex tried to organize these in a way that we can kind of have some structure. So let's start out with this one. So why is identification of input and output nodes by a user necessary? Because compile time only. And so this kind of deals with when you build a task, you define the template type for the task. So how I showed you in the graph instance where you define the output and input type, every task you define the output and input types. And for Hedgehog's case, you can have multiple input types, but only have a single output type. However, you could attach a task to multiple other tasks that receive the same output type for that task. So it could effectively broadcast to it. But the way that it would work is if you have multiple input types, then all you have to do is implement the execute function for the task for each individual input type. Now, we don't wait for all of the input types to arrive before firing the task. We will immediately start running as soon as any of the inputs have been received. So we don't have any dependencies between inputs. It's just completely asynchronous in terms of as inputs come in, it will fire the node and call the appropriate execute function for the input type that it received. And now, anytime that the task within the execute function calls add result, it will produce that output immediately to the next node. And so that has its own process, which I'll show in just a second. We require these node templates to be defined. It's mainly because we're using traits to kind of check compatibility. This is both true for the graph node as well as individual task nodes. And so if you were to try to connect nodes that aren't compatible, then it will complain at compile time to kind of let you know like there's some incompatibility here. By the way, if anyone has any questions as I'm going through this, feel free to chime in, and I'd be happy to provide more details as things come up. All right, so the next question that we got was, push does not preclude a pull model. How do tasks create data and generate work? So on the right here, you can kind of see the interaction between two tasks and kind of how the tasks operate with each other. So if you have a task 1 running on its own thread, it's going to be in an execute phase. When it adds result, that effectively will broadcast to all outputs that are accepting the output, which will then store result in a queue, which is attached to task 2. And then it will wake up that task, which is just to signal it to stop waiting and check the input. Now, the task is effectively looping infinitely while the queue is not empty, and it will process any item that happens to be in that queue. And so it will wake up, pull the data out of the queue, call execute, and maybe it's calling add result as well to kind of send data to the next thing, and it will kind of keep on doing this until the queue is empty, at which point when the queue is empty, it will go back into the wait state, or if it can deem itself as can terminate, then it will shut down the task. And the can terminate I'll get into in just a little bit.
So sorry for not remembering this, but the relationship between a producer and consumer is defined not only by the type, as you've outlined here, but a declared producer-consumer relationship also.
I think you
that has to be
CJ.
explicit, right?
Or sorry, you were breaking up a little bit.
Sorry about that. I'm not sure what to do about it. Am I still breaking up?
No, you sound better now.
I'll try again and speak slowly. The queue that you go into is defined not only by the type, but also by a compile time declared producer-consumer relationship. True or false?
Not really. If you do remember the code that we've shown earlier, this duality is declared with the add edge function. That's where you explicitly say, I will connect this task to this one. The library itself, when you will do this kind of edge, will create a queue for storing a specific type as the first output and the second input. They have to be compatible. So you, as an end user, you won't create this queue, but you will define this pair when you will just do the add edge. Does that answer your question?
Yeah, that's consistent with what I was attempting to say. So yeah, you don't create, it does get created, but the user doesn't explicitly create it, obviously.
Exactly, yeah.
That's
and if you've got, sorry, go ahead.
So one of the concerns that I would have is that if you basically think of defining an error handler, right? I'm gonna declare a condition, and I want this action to be taken if that condition is satisfied. When I write that error handler, I have no idea. The code hasn't been written yet for all the possible cases and places that could trigger that condition. And so how do I end up making that work? If I could have an uncountably large number of potential producers for this consumer.
Okay, so basically a queue is linked to a type. So if you've got a task that have multiple inputs, you will have one queue per type. So if you've got multiple producers that will produce a specific type for a specific task, that's totally right. They will be all sending their information in the same queue. So you won't know where they are from if it's where you're going. That's totally true, except if you've embedded into your data the source, the producers, an ID, for example, something like that.
Yep.
So that's something that you will need to think ahead in as an end user. If you've got a lot of different producers and you want to know where it's from, yes, you have to embed it into the data. In terms of general way of thinking it, we are just thinking in terms of data flow. So at the moment, the data is flowing through a system in a consistent way, we are good. Because we are thinking in a general way. If you need to do something in your data, or if you need to know the source of your data, you have to have some kind of ID or something like that, just to know where it's from.
Sure. In my question, I wasn't so concerned about the particular source of it, but I was concerned about the case of where I could have 100 places in a large app that could potentially lead to an error condition that needs to be handled. I think that you're saying that, and if I have a certain handler in mind, I can't simply describe in the consumer side, here are the conditions under which I should be triggered. In addition to that, for all the potential producers that could need that error handling, I must declare an edge to that error handler. Otherwise, it's not hooked up.
Yeah, you could broadcast the output of a particular item and then check for errors. That's one thing that we were thinking about in terms of checkpointing. If you wanted to checkpoint a particular region in the task, it would be possible to kind of just broadcast. So you just kind of connect an edge from the task to your error handling task, I guess would be the way I would handle it. And then that would be a way of checking if there's any errors in that when it's operating on that task. And depending, hopefully the error handling wouldn't be
task
too
as a whole, not specifically at a given program point that could actually have produced the error, but just the task as a whole. And so it'll know, hey, if this type, which could be an error type or something, shows up, wherever that happens in this task, that's okay. I know how to handle it because I've declared an edge from this task as a whole to the error handling task. That makes sense.
Right, you could definitely do that.
It's a little bit of extra overhead, but it's better than doing it in the 27 places inside the task that might have caused the error too.
Yep. I mean, it depends on the implementation and the application that's needed, but it would be possible to kind of create an error handling task where it checks the data for any errors, so you can kind of decouple that. And there are some challenges with that, but that's an interesting use case. And I'd be interested to kind of expand on that in the future. Because when we add a result, it will broadcast to every task, for example. And so to have like a mechanism for kind of doing error handling that's outside of the task, like independent of the task, that would be very interesting. We have done advanced things within the queue, such as doing priority queues, so you can have prioritization of the data in the past. It might be also interesting to expand on the queue so that it could do error handling within the queue itself. So when it gets a piece of data, maybe it does some error checking if you want to enable that kind of feature. And that could be like a new customization for the queue. So that'd be another way of looking at it as well.
Okay.
So just throwing out ideas.
This particular question was going after something in the other direction, though.
Okay.
But maybe you're still going to address that. This is more about work creation.
Yes, I will get into that certainly. Actually, I think right here, possibly. Can a task have many out edges that get triggered prior to the completion of the whole task? For example, could split vector task let a batch increment task that no longer subdivides start working as soon as 1/10 of the work is there, i.e. the first? So we are completely asynchronous in Hedgehog. So we will begin executing as soon as data is available in these queues. Now, the way that data gets added into these queues is via add result from within the execute function. And so the way that works specifically is as soon as you call add result, it's going to push the data in a FIFO fashion into the input queue for the successor task. Then a signal is called to awaken the thread for the successor task. This will immediately wake up that thread based on the OS and how it schedules the threads. And so as soon as it gets awakened, it will dequeue the data and invoke its corresponding execute for that what that task is doing. Now, if we have multiple outputs for a given task, they all have to share the same type. And as soon as you call add result, it will broadcast to multiple queues so that every task that's been connected to that output edge will receive essentially a pointer copy. So it will kind of share the data between the multiple tasks. And also we can call add result multiple times within the task. Every time you call add result, it will enqueue that element that you call add result with and do another signal. So every time it will signal more data. is there. Okay.
So I have a question.
Yes.
What do you do about scheduling and flow control in this? If you've got concurrent producing and consuming at the same time, then maybe you need to throttle the producer in some way, or if you have multiple consumers concurrent, then maybe you want to prefer the scheduling of one over another. What are the controls that are available?
So we have a memory manager, which will provide control, so that's entirely based on kind of memory allocation. It could also be based on like number of elements as well. It doesn't have to be bound to an allocation necessarily. It could just be kind of a blank item, for example. And that will throttle the task by means of a pool of this data. So if the pool is empty, then the task will block and wait. So it can't produce any data. And the reason for that is, in most cases, when we're doing like I/O and memory allocation, if a task is just doing that over and over again, and the compute tasks are extremely more expensive than this allocation task, then you're going to easily kind of oversubscribe the system and run out of system memory. And so the memory manager prevents that by having a fixed size pool. And the way that the pool gets reinserted is by means of a task later in the graph, which will release that memory back to the memory pool, which will signal to the task to wake up, to consume more memory.
I see. So the act of calling add result requires some memory from this pool for the result to be carried on. And effectively my add result gets stuck waiting on that pool.
It's even before the add result. There's a separate function that's like get memory from the memory manager. And the memory manager can be thought of like as a tool that can be attached to a task if you want. You don't have to have it attached. And that's just a mechanism for kind of restricting how many data elements are being produced from that task.
I see. So the throttling is sort of a resource starvation rather than an intentional sort of backflow of signal from the consumer.
Correct. Yep.
Interesting.
Yep.
Thank you.
And there is the potential for deadlock if you're not careful in how you manage the memory. So for example, you can apply state onto the memory itself to say, I want to reuse this piece of memory like 10 times. Like I don't want it to return to the memory manager until I've used it 10 times. And so if you don't define that well, then that memory might never return back to the memory manager, at which point then that task's deadlocked.
Yes, I can see how that would happen.
Tim, you may want to talk about the fact that we do not have a scheduler, and that while we've experimented with priority queues, but in most of the work, we haven't had a need for this.
Yeah, the benefit of the priority queue was more of numerical reproducibility. We did this with a computational tomography algorithm we were developing, and we just wanted to make sure the results were bitwise accurate, and the priority queue helped with that. But in terms of scheduling, yeah, we don't have anything that's interacting with the graph itself outside of just the queues. So the queues themselves and the flow of data is what defines the schedule entirely. And so as soon as you produce data, the system will just operate on its own without any need for anyone coming in and poking at it.
Interesting, because I can, if my schedule goes breadth first, then I consume more resources than if it goes depth first, for example. So how would I manage as the excuse me, as the developer, would I just have to produce somehow in a depth-wise fashion to avoid going too wide and exhausting my system memory at a higher tier of the application? Like it seems I might want to have some control over this.
So you'll need to understand what is the memory behavior of the algorithm. So how does it interact with your memory beforehand? And this is something, just an intuition that you need to have when developing an algorithm in the system, because understanding how is memory consumed, how is memory released throughout an algorithm is going to define what are your release rules, as well as defines what is your traversal strategy for the data. And I'll show a brief example of that a little bit later on with matrix multiplication, where if you switch from an inner traversal to an outer or from an outer traversal to an inner traversal, the memory access pattern is very, very different, such that you can oversubscribe the system memory, because you're going to need to reuse that data more often, or it won't have an efficient way of releasing the memory is really what it is. Because the outer product traversal will allow for, you just need to go through the outer product once, and then you can release that memory that's associated with the outer product completely. Whereas the inner traversal, you have to go through all rows of like an input matrix before you can start releasing memory, essentially going through the entire matrix before releasing some of that memory. And so that affects the performance of systems, as well as potentially affects the feasibility of executing the graph if you aren't careful in how you manage or represent that memory.
Yeah, interesting.
And we were starting to think that parallel programming wasn't hard.
Well, I mean, I think that this is exposing the issue with getting performance. Right, because everyone needs to think in this way to get real performance, because locality is super important in terms of getting any bang, especially on like GPUs. And so by forcing someone to think in this way, you actually get the benefit of getting better performance, because then people can kind of understand how their memory is local to their hardware, and when do they need to think in terms of when do they need to either save it to disk if they're running out of system memory, or when do they need to copy it back from the GPU if they need to kind of free up resources for some other operation. So although it is definitely a crutch because it requires you to think a lot more, but I think the thinking is in the right direction in terms of how to get performance out of an algorithm.
Yeah, I mean, that makes a lot of logical sense. It's a data flow model, and therefore the the flow of my data is what manages all of the execution. That seems very reasonable. Thank you.
Yeah, absolutely. Good, very good question. Thank you very much. All right. So could push data have been simply a data movement node? So we weren't sure what was meant by data movement node. But I'll talk about what our data is. If someone wants to chime in on what is a data movement node, I'd be happy to get some understanding on that. But the way that we operate is if a task is producing data, and you have a cluster or a group of tasks that are going to be, so that if you're multi-threading this task effectively, then they're all going to share that data queue. And so the data that gets pushed into this queue will essentially copy the pointer into the queue. So it won't do a deep copy. And then it will wake up one of these tasks, one of these instances, to kind of take that data and begin working with it. And so while one task is running, another element could have been pushed to the queue, and then a different thread might wake up to kind of begin processing a different piece of data, for example. And then this is true if you have two different tasks that are not grouped together. If you kind of add an edge between T1 and T2, and then add an edge between T1 and T3, and they share the same types between these queues, then what you're going to have is two different queues. And when you put add result, you will copy that shared pointer into both of these queues. Now you have to be careful, because if you do this, then you need to make sure that T2 and T3 are not going to be read and writing to that pointer, because then you'll have a race condition in terms of read-write races between multiple threads. But we leave that entirely up to the user to figure that out. Although I know Alex is looking at static time analysis at compile time to understand the structure of the graph at compile time and try to detect some of these conditions. And that's part of his PhD research.
Yeah. Also, if you want to be sure that you don't have these read-write race condition, you can just put some const variable. In this case, you can't write anything into it, so you have to duplicate the data if you need, and then be able to produce another one as a task.
All right, so we got a question about our matrix multiplication. So just to recap on the matrix multiplication example that we gave.
Do you want to pursue that last one a little more, or do you want to keep going on?
If someone has any
about
input,
the data movement node.
Yeah, does anyone here have maybe the person that asked this question?
Yes. Hi. I have a quick question. So you said you don't do the deep copy of the data. You only copy the pointer. So how about when the T2 and T2 and just read the same thing of the memory, and there is only one copy of the data? So what if this happens?
Right. So yeah, go ahead, Alex, please.
Oh, okay. Basically, T1 will just push one data, so you will just have one copy of this element into the queue. So T21 will get this copy, T2N won't have it. So the T21, if it's executed in order, T21 will get the first element, and T2N will get the nth element. They won't have the same element.
Oh, so they get a different. Okay. So the data. Do you mean they get a different pointer?
Yeah, they will get different data. Exactly.
Okay. The data is stored in different places, right?
Yes, you'll have different pointers for each data. Yes. So anytime you add result, you'll have a shared pointer. You could call add result on the same shared pointer multiple times if a user were wanting to do that for some reason, and then you'd have the same pointer multiple times inside that queue.
Okay. Thanks.
So part of where I think I raised the question about the push data and data movement node. Suppose you wanted to go have a task that would go pick data from some place and push it into the system, right? So this is sort of about how your data stimulus works. You could have read it, for example, from a file, and that action of once these conditions are met, then go grab the data and make something happen. Couldn't that also not have been, or how is it done as one of your asynchronous actions, to use HiHAT terminology, of just yet another node that is responsible for generating or pushing data?
Absolutely.
Is that something you already have, or?
Yes. So a task could be, for example, attached to a file. So when you construct that task, you could pass the file location, and then you can read from that file. We've actually developed a library built on top of Hedgehog called FastLoader. And the way it works is if you have, for example, a tiled formatted data storage on disk, then it will read the tiles in an efficient manner. And then as soon as a tile has been read, it will push the data to the next stage. And so this will kind of create a stream of these tiles that gets fed into the system. So it kind of copies it from disk into memory and then gives them a memory pointer. This could also be attached to something like a socket as well. So if you wanted to like have a network socket, you could be reading like packets, for example. And then once you've built a packet, you could copy that into memory and then offload that to the execution effectively, and then allowing to kind of go back and read the next packet without having to wait on the processing.
But that is there any utility for having a different kind of node as opposed to having an execution task that that does add result in it? Your answer may well be no.
I'd say no. We don't have any specialization for that right now. Although you could create a task that specializes that. I mean, FastLoader is kind of a generalization of just loading arbitrary different types of file types. So you have a loader that's attached to a specific file type. So we have, for example, have a tiled TIFF loader that allows you to kind of read that type of file. You could also have an HDF5 loader. So you can kind of specialize it in that way. So you can create like a repository of these tasks that could be reused.
Okay.
But we don't have anything built into Hedgehog though. All right. So as I was, does someone else have a comment? Sorry. No. Okay. So from the previous HiHAT talk, one of the use cases or experiments that we ran was matrix multiplication. And what was unique about that implementation is it provided a streaming kind of mechanism for the operation. And so the way that streaming operation worked is as soon as a result was ready, it would produce that result such that like a block, a subregion of the matrix could be produced as soon as that computation is done. And so the questions relating to that. So there are two metrics that we presented in the last talk, which was the first block time and the average block time. And so this is trying to clarify what those mean. So the first block time is essentially related to how much time does it take for that first element to be produced from the operation so that the next stage can begin operating on that subregion of the result. And so that provides us kind of an idea of how long you have to wait to kind of fill the pipeline if you have multiple of these operations up and running. Because depending on the traversal of the operation, you can get results much quicker. And so we wanted to kind of display that. So we want to kind of keep things flowing and understanding the flow at which things are happening. And that also goes into the average block time, because that's the average time that every single block in the operation is going to be sent. So the rate effectively that the blocks are going to be streaming into the next operation. And so that is kind of like a way of looking at just I guess the rate. I don't want to say real time because we don't have any real time constraints at all. But it does provide some idea of kind of how often or how quickly do these sub blocks get produced.
So just to, so to get that straight in my head, this is overhead in the runtime for the next computation to begin, or just exposed latency in that first block because there is no data for the next stage to begin?
Right, so the next stage is going to be waiting for data from the first stage.
Right.
And so this is like the latency of the first stage to produce its first block.
I see. Yeah, there's nothing you could do about that, obviously.
Yeah, unless you get higher end hardware and whatnot.
Right, but I mean, it's like many sort of tiling algorithms and so on fan out. Your initial first few steps are always small and slow because you haven't fanned out very wide yet or something like that.
Well, you could one of the hyperparameters could be like the block size. So the block size would affect how quickly kind of the initial block get produced. So for example, if you're doing LED composition and you pick a very small block size, then the kind of initial Gaussian elimination that you apply on that very first block is going to be much quicker than like a much larger block size. Mm-hmm. And so that you can kind of tune it in that way potentially.
Yeah, I could see doing that. Okay, thanks. Yeah, I was curious what those two, what the gap was, but it makes sense.
All right, so terminology question. So finish pushing data tells it it to not expect any more data beyond what's already been received, so that worker threads can quit. So is this relevant for persistent kernels? And that's exactly right. So these are persistent kernels, and so they're going to live until the input edge has been terminated. And so the finish pushing data, which is called from the main thread on what we call the outer graph, will essentially decrement the edge to say that there's no longer anyone inputting data into the edge of the graph. And so the default behavior for the terminate of a task is it will say, are there no more inputs coming into my task, and is there no more data available in my queue? So if both those are true, then it can safely quit itself. It'll terminate itself. And that has like a cascading effect. So we'll do effectively a breadth first traversal through the graph that's kind of automatically going to be initiated based on that initial finish pushing data. And so it can kind of cascade down through the tasks as the queues become empty. This behavior can be customized. You can overload that can terminate function. And so the way that you could do that is you could just return, for example, return true. And if you do, then it will immediately terminate that task. But we use this for kind of dealing with cycles in the graph. So that if you have a cycle, you can kind of understand, well, how many times did that cycle fire? And one way that we do that is just like a time to live. And then once that time to live reaches 0, then we can kill that. And I'll give a brief example of that in a little bit. All right, so what are the multiple conditions that could trigger dynamic execution? Post a dominator act on a stimulus from a then or else clause of a preceding runtime conditional. So we don't have any kind of hard mechanism for, I guess, managing the full runtime. It's entirely based on the data flow and relying on the data pipelining. And so we don't have these kinds of scheduling behaviors built into the queues or into the edges. It's going to be entirely based on when does a task call the add result function to kind of initiate new data to the next task, and then what is the state So how is the state being represented for tasks? So that can also affect things when things get produced. So if you wanted to have like an if-else kind of condition, then what you could do is have like a state manager that says, okay, I want to kind of split based on these data types or something. I mean, hopefully I've captured what the question is. It's kind of a different scope, I think. If anyone wants to clarify.
Then you'd add an event, do an add edge from each of the then and else clauses to the post dominator that was the consumer. And
that's right.
The consumer would trigger after a single, and they both need to match in terms of their output, and the post dominator consumer would have to match in terms of the input. And then as soon as he's got his one trigger, he's done and good to go. And he doesn't care which of the various producers it was that produced it.
That's right.
And that's all good as long as it's mutually exclusive. If you had, if you could end up with multiple producers, and then that gets messy, and you need to understand that from a programmatic standpoint. Sorry, if because you could get ignored, and you can have race conditions and all that kind of stuff, and or trample or whatever. So like I'm thinking of a case where you could have a cascade of conditionals and then a consumer, and you could have some variable number of paths. It could be 4 paths that you could take through that, and you could get from 0 to more than 1 triggers, and you have to know how to deal with that.
Right. So
if you had somebody that dropped something into in an algorithm where you're sort of looking for the first instance of something, and somebody else says, well, hey, here's another thing for you to look at. Do you have a mechanism by which you can say, hey, I don't care anymore, and I've already consumed this queue, I want to close up the queue, and if somebody else tries to drop something into it, then ignore it, drop it on the floor, and don't consume any more resources?
Yeah, absolutely. So you could overload the can terminate, and once you've gotten that special condition, you could then return true from the can terminate, and it will immediately terminate even if there's data in the queue. So you can kind of control.
I guess I'm thinking about the case of if after the first consumer has come along and grabbed something out of a queue, and the desired effect is, I don't care about anybody putting anything else in this queue because I've already got what I want. Then how do you handle that with respect to the next producer that comes along and tries to shove something in that queue? Because one of the things you could do is to say, look, really, I don't care, eliminate the queue is gone, and now the producer tries to shove something in the queue that doesn't exist anymore. What happens?
I mean, we don't have any explicit control over that. I mean, the only thing we know is if they terminate the edge for a particular consumer, then if there's a producer that's still producing data into that edge, you'll still be producing data into that edge. It just won't operate on it in that case.
But does it use resources?
It will use pointers. It will allocate pointers, potentially, if you have a different shared pointer for each object that you're inserting into the queue, and essentially that queue is going to build up in size.
And how does it get cleaned up?
It won't until the end, until it's no longer being referenced, I guess.
Yep.
The shared pointer will.
Yeah, when you will lose scope of the graph, you will clean everything, the data, the queues, the tasks, everything.
So maybe one thing that would have to happen is the producer has to have some knowledge as to when it needs to stop producing as well, so that it knows that it's received the item that's going to kill the consumer, for example. So you'd have to, I mean, if you want to prevent that, you'd have to instrument it into the task implementation itself.
Okay.
All right, so we got a question about feedback. Sorry, do we have any other questions on that? Okay, so feedback, which is our profiling mechanism. So we have profiling at the task level, and so we don't have any cost to that. We actually did some statistical analysis on that, and you can kind of see the distribution here. Yes?
I'm sorry, I couldn't think of another question here before I go on, before I lose too much context on it. it would be, you talked about a way that you could have the producer signal back to the consumer signal back to the producer to say, hey, stop producing because I don't care anymore. That could
do that.
Potentially, that smells like a cycle in your graph. And
you could have external factors beyond the graph itself to control that as well, which I've done in the past, where you kind of share a piece of data, like maybe an atomic value between the two tasks. And so you atomically increment that value, and if that value equals something special, then you can tell it, okay, I don't want to deal with this anymore. And so you could do that during construction of the tasks. And you customize how the tasks get cloned as well, so that you can share that data among all the threads if needed. So you can share data between tasks if needed. That's outside of the scope of the graph.
Okay, and then does it cause particular problems if you would create a cycle in your graph like that? If you declared a dependence, an arc back from the consumer back to the producer?
The graph wouldn't know too much. I mean, as long as you have a good structure in your graph in terms of when it gets terminated, so it doesn't deadlock, then it should be fine. We don't have any detection on that, like in terms of what variables are shared between tasks if you pass it into the constructor and have like an instance variable inside the class.
Yeah, I was talking about if you stuck with using explicit dependence arcs and add edge going back,
right? So
in the other direction.
You could absolutely do that. And so if you have a specific type that's being produced, but you have to keep in mind it's only one output type, so you can't have multiple output types. So that task would be responsible for kind of signaling back to the producer, I guess, and it would be on its own execute
task can only have
function.
exactly one output type?
Yes.
I missed that.
Yeah, so you have one output. It is, and that's one thing I've been discussing with Alex, but we've been pretty strict on that. We're not sure if we need multiple output types at this time. The challenge there is the way that templates are defined. If you do variadic templates, then it's everything out after something. And so we can't distinguish between input and output if we do variadic of both input and output.
Yeah, what we had in mind is basically when you call the C function, the C++ function, you just have one output type. You can have multiple inputs, but just one output, and that's something that we want to keep and have. And Timothy is totally true. So at the moment you've got a template parameter pack, you can't have multiple parameter packs because the compiler, or you won't be able to discriminate which one is which. So we need to have one list and one single or multiple singles, just to be sure that this one is represent this information and this one represent this information and this pack represent that. That's why we have the output in first when we declare the template, because we just have one output type and the rest are all the inputs.
And one strategy that we've done in terms of expanding the output type so it can handle multiple different types is by having kind of a superclass that holds onto multiple types and then have like an enum type within it so you can switch between the different types. We try to avoid that when we can, but if you can't get around that, then that's another option. So you could have multiple constructors so it builds the different types.
Yeah. Thanks.
Okay. Yeah, no problem. So we did, so you can see that in this graph, when we enable or disable profiling in the system, we really can't distinguish between whether it's profiling or not for larger problems. And the overhead is quite small when you enable profiling, such that the way that the pipeline on the CPU operates, it's able to kind of hide the cost of kind of incrementing the values when you're counting like what is the execution time or the wait time for a given task.
Should we, given where we are in time, maybe we want to pause here?
Sure.
I think you have some more responses, and there are more things that we could get into in terms of some of the other things that others could learn from state management, memory management, data as a first-class citizen,
sure.
and other items.
Jump to
and that. Well, I'm just saying we're out of time. We got 1 minute left. we could just continue this next month if you're up for that.
Yeah, sure.
Yeah, absolutely.
And
that sounds
we'd
great.
be interested in hearing your. I sent you some presentations that we'd actually given before here of some things that could be relevant, and be interested in your reaction to some of those things on profiling and other items.
Yes, and I've looked through the slides on that, and it is very interesting. It's a very different way of going about it. I mean, I know Wally has some interesting points on that. If Wally, do you want to chime in?
Yes. So this is Walid. I mean, the HiHAT work is impressive in its scope. It's very ambitious. We are, once again, I mean, we are driven by sort of the kinds of applications that are on our to-do list, and they're mostly imaging related applications. And these are the kinds of images that we typically extract out of, or we get out of instruments. But sort of one of the decisions that we very early on took is that we will only instrument the task graph at the level of tasks, and we allow other tools to instrument the rest of the system. So if we want to instrument compute kernels that are running on the GPU, we're going to use Nsight. If we are instrumenting compute kernels on the CPU, then we're going to use profiling tools that are available on the CPU to instrument things on the CPU. This is why, I mean, for problems that are of a particular size, sort of once we go beyond the trivial problem sizes, whether we turn profiling on or off, from a statistical point of view, I mean, so we cannot distinguish whether it's on or off.
So we do need to wrap it up. Sorry to cut you guys off.
Yes, absolutely. So I mean, again, I mean, we're willing to do this next. We're willing to continue next month, and then hopefully we can sort of clarify sort of further how we do things.
Sounds great.
Excellent.
Thank you very much, guys.
Happy to follow up offline too, but yeah, it was very interesting. And
yeah, very interesting.
You've been very systematic and diligent in going through this, so thanks so much for that.
Yeah, thank you.
No problem.
Thanks, everyone.
And feel free to communicate with us if you have any more questions.